So, welcome to the last session of this wonderful conference. I request Professor Shauli Gun to chair the session, the concluding session.
Welcome back, everyone, and let us invite the speaker, Professor Jean-Marc, who has been visiting us, I think, from the time, I think, the beginning of the institutes, or almost. And I mean, I don't need to introduce him because all of us know him really well. And I request Professor Deshouillers to speak. His topic is number theory and probability.
So I would like first to thank the organizers and for giving me this opportunity to be back to Chennai. As you know, I like very much to come to India and to visit Chennai, and now I have several collaborators, friends, and so happy to be there. So thank you very much for this invitation. Indeed, there are two essential people who are responsible for my coming here and loving here, and they are present here. One is Balasubramanian, and the other one is Krishna. Well, the first reason is a mathematical reason, because we had been working with the Balu on something that was an old problem, and we succeeded in doing it without never meeting. It was published in the early 86, and we never met before. And for young people, you must understand that at that time there was no email. Even telephone was something very complicated. Even telephone inside India, you should remember that at that time you had to book a phone and wait for a few hours before you could get something. And so everything was by ordinary mail. And if it is with someone who doesn't like too much to write, it was a bit complicated, but we did it. And also, this is the part of Balu, and we are still working together. And the White Krishna, it turned out, and this was really, really great, that Krishna visited Bordeaux in October 86. And I had a visit which was planned in India in beginning of 87. And Krishna was wonderful to organize all my trip over India and visiting several places. And really, thanks again. Without you, I don't think I would have this connection with India. And of course, one of the stop was to stop at. Now I have to read it. Ekamra Nivas. Okay. And I was invited by Aladi Ramakrishnan, and I was invited to give a talk for not grown up in someone number theorist, but a general audience, and also there were a lot of students. And one of the students was maybe 13, 14 at that time, very interesting guy, and raising several interesting questions, and very, very acute on everything. And this guy is still Kanan Sundararajan, who is a well-known mathematician, first-class number theorist. So, so now we have to go into the business. So, what to talk about? I have noticed that this was not only for number theorists, and I am not going to talk for number theorists, but also physicists were here and are here. And so I thought that it was maybe to explain something about what I am doing, but in a way that could be understood by several people. And I am now thankful to Ram Murthy for two reasons. First, to show me these things. Okay, how to use that? I don't know. It is the first time I'm using that, you see. Before that, I say, I would like to have some chalk and how to erase. And I was provided with everything, but I tried to use this, which seems more comfortable. Okay, and also for a second point, it's about what is number theory. Contrary to many other fields, number theory is defined by its object and not by the methods. The object is just study numbers. And what Ram was giving is a very good example. You take a summation of what can be the sum of the inverse of the GCD, PPC, least common multiple of lot of numbers. And this is a question you can easily understand what it means, but to solve it is something different. And in number theory, we're using different methods. One method is, of course, you have some algebraic tool. By the way, already prime numbers are defined by the algebraic property of the integers. They are you can factorize. They are the bricks in the multiplicative constitution of the integers, and you can raise a lot of problems. By the way, even some problems which are not solved nowadays. And for example, if you think of that there are infinitely many primes. So you have the algebraic solution, which was given already by Euclid, and which said that, well, give me, it was not to say infinitely. Greek would not accept this notion, but they would say, okay, give me all the primes you know, and I show you that there is another one. And we know all this proof. You make the product, you add one, and you say this number is factorizable, and no prime can be in the other thing. But there is also another way, which is the way Euler did. And now you are familiar with this. It's you take this series, 1 over n to the s, and you write it as a product of all the primes of 1 plus 1 over p to the s plus 1 over p to the 2s plus and so on. Okay, so if you look at it without taking care of convergence or something like that, this is just an algebraic way to say that if you take an integer n on this side, then this integer, yeah, you don't see it. This integer will be the product of powers of primes. Now, if you know a bit more, that is to say, not maybe for student at school or high school, but maybe first-year student, you may show that this converges if S is a real number which is larger than 1. You have convergence. Well, first of all, this is not really important. Another way to do that, to erase that, is to take the inverse. But essentially, this is the right order of magnitude. And now what Euler did, which is great, is to say, okay, this converges, but now we want to do analysis. Analysis is always to try to go where there is a problem, where there is a singularity. I think in physics, this is also what you like to do, is to know where there is a singularity. If everything is smooth, there is nothing really interesting to say about. And you let S tends to 1. Now, if S tends to 1, this, you know, it is the harmonic series, and it diverges. So the left-hand side should diverge also. But if there is only a finite number of prime, you see this product is really, all the terms are really nicely convergent. If S up to is positive, this is enough. So if you have only a finite number of prime, then when S tends to 1, the right-hand side is going to have a limit, finite limit when S tends to 1. And on the other hand, it will have infinite limit on the left. And so you have infinitely many primes. But this gives you even more. This tells you something, that the sum of 1 over p diverges. And this tells you that there are really many primes, more primes than squares. Okay, so this is for that, and now I want to talk about something different, which is probability theory. And there are several reasons for probability, because I like probability and I'm using probability in my studies in number theory, but also that probability was a field of one of the fields of Aladi Ramakrishnan. And so it is for, as a, say, well, as a tribute. Thank you. As a tribute to Aladi Ramakrishnan to talk about probability, also connected with number theory, which he liked also. Okay. So, now there are two ways to use probability in number theory. One way is to say about multiplication, if you take the probability that a number is divisible by 2, you can say that this probability, let us think of density. You see, making a measure on a countable set is difficult because measure cannot be diffuse. They have to be atomic. And this makes that there is no really interesting measure on numbers. But if you think of density, you count the number of elements up to x, you divide by x, and you see what is the limit. You have a density 1/2 for elements which are divisible by 2, and you have a density 1/3 for elements which are divisible by 3. And if you are looking at the intersection, the number which are divisible by 2 and 3, then the density is 1/6, because this is the numbers which are divisible by 6. And so you have something that tell you there is some independence, because the density of being divisible by 2 and the density being divisible by 3, if you take both at the same time, it would be the density to be divisible by 6. And this is not true for any number. 2 and 3 are fine, but if you take 2 and 4, it doesn't work. If you say for 2 and for 4, density will be 1/2, density will be 1/4. But if you ask that they are both at the same time, of course, being divisible by 4 is enough to say that you are divisible by 2. So this will be there's no independence, and you see that independence in when two elements are coprime, and you see something immediately. Again, I'm referring to the talk of Ram, that you have something which is called multiplicative functions. Multiplicative function will be if they are divisible by, if f of mn will be the product of f of n and f of n. So this, you can have some probabilistic understanding of that, and indeed this was one of the first results is due to Ramanujan in accounting the number of divisors you have, and to say that you have some behavior as if you were adding random variables. And a bit later you had also, and Aladi Ramakrishnan has been working on that, on Erdős-Katz result. And Erdős is essentially a combinatorist and number theorist, and he became probabilist, but at the beginning he was not probabilist. And if you have Erdős-Katz, it's because Erdős had some question that should look like, let us say, Gaussian law or something like that. And then you say there is some Gaussian law, but he raised this question, and fortunately Katz was here, the great probabilist, and Katz said, oh yes, but I have the tool for that, and this is how they're connected. So you have a lot of results. By the way, if you want to know, if you don't know, if you have not seen Erdős, you can see it on the different pictures that was given for the conference. It is in one of them. By the way, the one which is just before the one with George Andrews was giving a talk yesterday. So this is the multiplicative side. And I'm not going to talk too much about that, but maybe to talk about the additive side, which is maybe less known. So I would like just to give one example for that. So let us give one problem of Zidon. Zidon was the following problem. Zidon's problem. Zidon's problem was the following. Well, I write better on the board, but okay. Zidon's problem was the following. Zidon was working in harmonic analysis. And harmonic analysis, of course, you go immediately into Fourier transform, and you know that Fourier transform are a nice property, because if you have the sum of random variables and you look at the Fourier side and you make their convolution, on the Fourier side, you'll get simply a product. That is to say that what you get is something which is exponential if you have integers of 2 pi I. Well, 2 pi I is a nice Fourier transform if you are dealing with integers. exponential of 2 pi I a plus b. It was the exponential of 2 pi I. So we are going to write it quickly. This is exponential of 2 pi I a times exponential of 2 pi I b. Okay, this is just, this e of a means exponential of 2 pi I something. So this is, you have this product, and this is important, and so you have, he was interested in knowing what can you say about this set of elements. So you have the following, you have A, which is a subset of n, let us say A1 less than A2, blah, blah, blah. And this is a set included in n, at least the Bourbaki n with a 0 inside. But for what we are doing, it's not a real problem. You can always add 0 at the end. It is not a real problem. So you have a set A like that. And what is your interest in? You are interested in looking at R2 of n, R2 of n, the integer n, will be the number of representation of n at the sum of two elements. So this will be the sum when A, B are in A, and A plus B is equal to n of 1. So you are counting these numbers. And Sidon, for his problem, was interested by what we call additive basis of order 2. He was interested in set such that every integer can be represented as the sum of two elements. That is to say, what Sidon was interested in is to find A such that R2 of n is positive for every n, but also he wanted to have something which is economic. You don't want to put too many elements in it. So he wanted something to say, let us say this is a big O of n to epsilon for any epsilon. You don't have too many. Okay. So what you could think to be a good candidate would be squares. But squares do not represent everything. Landau, in the beginning of the 20th century, proved that the number of elements up to x, which are sum of two squares, is something like x over square root of log x. Okay, not too bad, but you don't have all the elements. But for the sum, it's for the upper bound, it's fine. So this was the question raised by Sidon. Can you find a sequence having those properties? And this was solved about 20 years later by Erdős. Erdős in 1956, I think, or 55, showed that there exists such an A. Answer is there exists A. Now I would like to give just a hint of the proof of Erdős, because this is typically what you do, a typical way to use probability theory for a question which is typically a question in number theory. So the question is to say Erdős was introducing, he was a combinatorist, and he has been also using this type of random sequences, random graphs, something like that in combinatorics. So what you try to do is some random sequence. That is to say, what you want to do is you are taking dice in some way, or coins, and you are throwing your coins, and you say, this helped me in producing a sequence, and what I want to say is, among all the sequence I am producing, there is one which has this property. So how do you do that to toss a coin and to have a sequence? Well, what you define a sequence of psi1, blah, 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 psi n, blah, blah, blah. Those are random variables with value 0, 1. So in some way, each one, psi1 is the result of tossing the coin number 1, psi2 is the result of tossing the coin number 2, and so on. You see, you have several possibilities because 0, 1 times 0, 1, 0, 1 is something which has the continuous, it's not at all countable, although the number of elements you have is countable, but if you are looking at countable, 2 to the power countable, then you have something which is pretty large. And so you can make probability on that. Okay? So you want also them to be independent. It will help for computation, and it doesn't cost nothing more. So you have this set of random variable, and now, so you see, each time you have a big bag with coins. You have a countable many coins, but it's okay, and you throw them. Okay, and each time you throw them, you say this is an element in a big set, the set of all the choices which are possible, the universe for probabilists. And so each time you take a little omega, that is to say, each time you make some experiment and you throw it away, you have a set of zeros and one. Now what you say is that, okay, I am going to define A of omega to be simply the set of n such that psi n of omega is equal to 1. In some way, you see this psi, which have the value 0, 1. When you make an experiment, you have a sequence with values 0, 1, 0, 1, 1, 1, and so on. And you are taking, okay, my set will be the set of integers for which the psi is equal to 1. In some way, this function of omega will be the indicator function of the set A. Okay? So this permits you to find A, and this is exactly what is called random sequence, where to build a random sequence. So everything is defined except one thing. What will be, if you toss a coin with 0, 1, with the equiprobability 0, 1, it will not give you much. So this is the trick. The trick is to know what can be the probability that psi n is equal to 1. This is the only thing to define now. You have everything, there are values 0, 1, and so to know what is the value, and they are independent. So the only thing to know is to know what will be the probability. So if you remember with squares, we were not too far from what was good. You think that something a bit more than squares could be okay. If you take too many elements, you see, then you will be in difficulty because you cannot have this upper bound here. The big O of n to epsilon, it doesn't work because you shouldn't get too many elements. So you have to find something which is close to squares, but not exactly squares. Now, what are the squares? What is the probability? If you select in some way randomly, let us say in the naive sense, you take randomly an integer, what is the probability that it is a square? Well, if you are around n, you have squares which are square root of n, integral part, and the next one will be square root of n integral part plus 1. The difference between those two is 2 times square root of n, up to big O of 1. It is 2 square root of n. So that means that the probability that an integer n is a square is something about 1 over 2 square root of n. Okay? So the probability would be something like 1 over 2 square root of n. Okay? And so this would be, if you take 1 over 2 square root of n, up to constant, I don't care about the constant. It's square root of something over n. If you put a 1 or if you put the 1 over 2, then you have exactly the squares. You want to put a bit more elements, and it turns out that with log, it will work. So you put log n over square root of n. So it is a sequence which is a bit richer than the squares. So then you have things which are easy to say that with all that, it's not too difficult. This is an easy exercise in probability to say what are the numbers of elements up to n, and the numbers of elements up to n will be something like square root of log n n. So this is the number of elements. But what is interesting is that with this construction, you can work a bit and say now what happens, what is the distribution of those sequence and of the sum of two elements. Sum of two is fine because you see once you have one value, you have immediately the other one, and you may assume that the other one is not the same. Forget about the elements which are just 2 times one element. You know that this will be peanut in the process. And so you have no question, there will be always independent. This is nice. You know that if you are tackling random variables, if you are independent, you are happy with that. So this is what you can get easily with that, is that to show that almost surely, that is to say, on a set of measure 1, because now you have a measure on omega, clearly, and for almost all omega, you will have the following, that R2 of n is something which is between C2 of log n and larger than C1 of log n. Capital N, if I put capital N, I put capital N here. Okay? And this is very nice, because what you wanted to have is to have something which is R2 of n is positive. Okay, it's positive. But for 1, you don't care. You add 1 and you are happy with that. And you want it to be big O of n to epsilon. You have much better than big O of n to epsilon. You have something like log n. So since this is true for almost all sequences, according to the measure we have, there exists one sequence for which it is true. And so this proved the result. And this is not too complicated. I mean, I'm of course hiding the work in probability to prove that. Now, just, I still have 5 minutes, I guess. So this was to give an example of this. So now this is an example in which, in some way, you show that something exists. It's not constructive. But you can work on that and transform everything which is of this kind, which is non-constructive, into something constructive, a possibility of doing that. Now, there is also another way to use probability theory, that there are problems, additive problems, for which we have no answer, or we don't know yet what it is. For example, what can you say about sum of 3 cubes? Sum of 3 cubes, it was not clear. When I first discussed that with Erdős, which was in the end of the 60s, Erdős was thinking that the density of sum of 3 cubes was 0. That you asymptotically, the number of sum of 3 cubes up to x is little o of x. He changed his mind later after. But there was also at that time some computation that has been done. But you have also to understand that the computation now you can do on your laptop, something which is infinitely more important than what could be done on huge computers at that time. And Barucan made some computation. And what he noticed the following: you make something which is, what can you say about this? Will be the density between 0 and 1 of sum of 3 cubes. And he was looking at what you get, and what he could do at that time was something about 300,000. Is it tending to something positive, or is it tending to 0? It's not that clear. Okay, especially that the terms you will have are terms which are log or log-log, you see, after having this. So, of course, now we can do much better. Now we can do better, and with François Encart, who's in Saint-Étienne, and Bernard Landreau. We have made several things at that time, and we could work until 10 to the 14, even a bit more. And what we noticed, there's something like 10 to the 12. So what we did is to find some probabilistic model for sum of 3 cubes. This probabilistic model would tell you, I don't say anything about the model, will tell you that it has a positive density, and this positive density is something which is about close to 0.099924 or something like that. Well, some value you can compute, and you get that, about 1/10. So you see, what Barucan did was to be above this value, so it didn't mean much. And so we were computing, but this takes time to compute, because computing additive question is long. So we were like that, and about 10 to the 12, it went below. this value. And fortunately then, it started to go a bit upwards. Okay? So we have now some impression that this probabilistic model is fine. So this is just to say that probabilistic model doesn't give you anything, doesn't prove anything. It is a theorem in probability, which has no interest for probabilists, but maybe it has some interest for some number theorists at least. And more recently, some Turkish guy, Altuk Altman, noticed that sum of all the factorials are sum of 3 cubes. What is the reason for that? And we used our model and could prove that in our model, almost always, from some point onward, the factorial has sum of 3 cubes. So in some way, it helps you. You see, it is what Alf van der Poorten, my late friend Alf van der Kaput was saying, van der Poorten was saying, there are 2 types of theorems. You have the theorems you have here and the theorems you have here. And so this theorem about 3 cubes is the theorem I have here. Okay, thank you very much for your attention.
Thank you, Jean-Marc. Any questions?
So are you saying that the density of the set of natural numbers that convert into a sum of 3 cubes is now 0.09?
Yeah.
That's a theorem.
No. It's not. No, it's not a theorem. There is a probability theorem telling us that something which seems to be a good model for that tells us that almost always it has a limit which is this value and the same value that the one we can compute and we can see experimentally. So we have 2 things. We have some experimental data on sum of 3 cubes. We can prolongate the model up to 10 to the 18. And so this is experimental data. We have a probabilistic model and we don't know anything. It's not a proof this time.
Is the connection to class numbers helpful? No.
No, I don't think so. Okay. We have to know what are the distribution. In our model, you see there was some model like that has been introduced by Erdős and Rényi in 60 for sum of, but it would tell you that for sum of 2 squares you have a positive density. So obviously this is not a right model. So we modified with Enkar and Landreau, we modified the model to take care of the fact that cubes are not well distributed into arithmetic progression. And we take this into our model, and in our model, arithmetic probability model, then we can prove that.
Any more questions, comments? I think you wanted to make it.
Yeah, just a brief comment. In his later years, Erdős would generally give a talk called Some Problems and Results in Number Theory, as you know.
Yeah.
And typically, one of the first problems he would start with would be the problem of a Sidon sequence.
Yeah.
And therefore, the Sidon thing was very much one of his favorites. So I'm happy that you actually started your lecture with the Sidon model.
Okay. If there are no more questions, let us thank the speaker once more.
I request Professor Balasubramanian to give this present as a mark of appreciation.